Hi everyone. Today in this video I am going to discuss about damped harmonic oscillations or damped simple harmonic motion. A pendulum will swing only briefly underwater because the water exerts on the pendulum a drag force that quickly eliminates the motion. A pendulum swinging in air does better, but still the motion dies out eventually because the air exerts a drag force on the pendulum and friction acts at its support point, transferring energy from the pendulum's motion. When the motion of an oscillator is reduced by an external force, the oscillator and its motion are said to be damped. I am repeating again. When the motion of an oscillator is reduced by an external force, the oscillator and its motion are said to be damped. An idealized example of a damped oscillator is shown in figure, where a block with mass m oscillates vertically on a spring with spring constant k. From the block, a rod extends to a vane, both assumed massless, that is, submerged in a liquid. As the vane moves up and down, the liquid exerts an inhibiting drag force on it and thus on the entire oscillating system. With time, the mechanical energy of the block spring system decreases. Yes, energy is transferred to thermal energy of the liquid and vane. Let us assume the liquid exerts a damping force Fd that is proportional to the velocity v of the vane and block, an assumption that is accurate if the vane moves slowly. Then, for force and velocity components along the x-axis, we have f of d equal to minus bv, where b is a damping constant that depends on the characteristics of both the vane and block, an assumption that is accurate if the vane moves slowly. Then, for force and velocity components along the x-axis in figure, we have f of d equal to minus bv, where b is a damping constant that depends on the characteristics of both the vane and the liquid and has the SI unit of kilogram per second. The minus sign indicates that Fd opposes the motion. Damped oscillations. The force on the block from the spring Fs equal to minus kx, where k is the spring constant or stiffness. It expresses the stiffness that's present in the string. Let us assume that the gravitational force on the block is negligible related to Fd and Fs. Then we can write Newton's second law for components along the x-axis as minus hv minus kx equal to ma. Substituting dv by dx by dt for v and d square x by dt square for a and rearranging gives us the differential equation m into d square x by dt square plus b into dx by dt plus kx is equal to 0. The solution of this equation is x of t equal to xm e power minus bt by 2m cos omega square t plus 5, where xm is the amplitude and omega dash is the angular frequency of the damped oscillator. The angular frequency is given by omega dash equal to root of k by m minus b square by 4m square. If b equals 0, there is no damping. Then omega will become root of k by m for the angular frequency of an undamped oscillator, and the equation reduces to for the displacement of an undamped oscillator. If the damping constant is small but not 0, so that b is lesser than root of km, then omega dash is equal to omega. Damped energy. We can regard equation 15 42 at a cosine function whose amplitude, which is xm e power minus bt by 2m, gradually decreases with time. For an undamped oscillator, mechanical energy is constant and is given by E equal to half kx square m. If the oscillator is damped, mechanical energy is not constant but decreases with time. If the damping is small, we can find E of t by replacing xm with xm e power minus bt by 2m, the amplitude of the damped oscillators. By doing so, we find that E of t equal to half kx square m e power minus bt by 2m, which tells us that, like the amplitude, the mechanical energy decreases exponentially with time. Thank you.